right? So yes, multiply by the numerator and denominator by the conjugate, and that's all. Yes, minus x squared and minus x squared. So what's going to happen here? Number one, cancel out the radical. That's going to leave us with limit x squared minus 3x minus x squared over this humongous radical here, square root of x squared minus 3x minus x squared as x approaches infinity. Alright, so notice that we can also cancel out these x squareds, and that's going to leave us with limit negative 3x over the square root of x squared minus 3x minus x squared. Oh wait, this is not x squared in the denominator, it's just x actually. Alright, x approaches infinity. Alright, so this one looks already like a quotient between two quantities, yes?
Is it minus x, not plus x?
Yes, it's plus x, thank you. Yes, plus x. I took silly mistake. Sorry about that. Alright. So, now that we have quotient of the quantities, I mean, we could do the L'Hopital's rule, but I mean, I think the L'Hopital's rule would be a little overkill with the radical and the quantity inside of the radical, you know? Because we would have to use the chain rule. We would end up with negative rational exponents. Well, I'm not going to be a huge fan of that. However, I'm going to use regular algebra to simplify, not the L'Hopital's rule. And well, so now let's have a look at this expression. The order in the numerator is degree 1. The order in the denominator, well, it's a radical, but I mean the highest degree term inside of the radical is 2. And the square root of x squared, that technically reduces to x to the first power. So there's gonna be a pretty cool cancellation in there. So I'm going to factor x squared from the radical. I know, how am I going to factor x squared if I have x squared minus 3x? I can't factor x squared from the second term. Well, we can actually. But it's going to look like this. And so that's going to be x squared times 1 minus 3 over x plus x. Alright, so, okay. If we distribute this x squared times 1, that's going to give us our x squared. And if we distribute x squared times 3 over x, that x squared over x is going to give us back the x. Right? So from here, we can write this product inside of the radical as the radical of two products, or simply take the square root of the perfect square. What's the square root of x squared? Isn't that just x? Well, technically it should be absolute value of x, because that depends on whether we input a negative or a positive value. However, we're going in this case in the positive infinity direction, so in this case no need for absolute value bar, so that's just x, root of 1 minus 3 over x plus x as x approaches infinity. Alright, now from here we can factor out this x. It's a common factor in the denominator, so we can write this as yes, we can be careful because we cannot cancel this x right here with that x, because this x is a factor of a term in addition to the x. So in order to be able to cancel x's, we need to factor it out first. So that'll be limit x approaches infinity. That's a negative 3x over x that multiplies the square root of 1 minus 3 over x plus 1, and only then divide out the x, and we may go about computing the limit of negative 3 over the square root of 1 minus 3 over x plus 1 as x approaches infinity. Well, number one, this term right here, where is it gonna go for x going to infinity? 0? Well, that's gonna leave us with the square root. In the denominator, it's gonna leave us with the square root of 1 minus 0 plus 1 outside with a negative 3 at the top. Negative 3. Okay, the square 1 minus 0 is 1. The square root of 1 is 1. 1 plus 1, isn't that a 2? Which is really instead negative 3/2. Alright? So yes, so this indeterminate form, infinity minus infinity, is not 0. It's actually negative 3/2. Alright? Let's have a look at another example, a very classical example in L'Hopital's rule. So for this example, or the next couple of examples actually, what are we going to have? We're going to have a function whose power is another function. This is the first time we see something like this. Well, actually no. We actually looked at this kind of functions when we did the logarithmic differentiation. Remember those? So when we took natural log on both sides to make that power a product, then we use the product rule along with what's it called? Implicit differentiation. So we're going to do something similar here. Alright? So here is the thing. When you see something like this, well, number one, let's check which indeterminate form is this. So number one, okay, so 1 plus 3 over infinity. What's 3 over infinity? Isn't it 0? So that's 1 raised to 4 times infinity. That's 1 to the infinity power. So that's one of the indeterminate forms. It's a weird one. Well, there's a way around. I'll show you how do we go about this one. Well, for now, this limit right here will be, let's call it y. Alright? It will be a number y. How about that? Okay.
Particular reason that doesn't just equal 1, because no matter how many times.
Exactly. Yeah, it's one of those mysteries, weird mysteries about indeterminate forms. Yep. So
there's no like rule proving it.
yes, because it's in infinitely many multiplications, right? I know it's 1 times 1 times 1 times 1. Yes, it's always 1, right? It's weird, but so let's go ahead. Y equals limit x approaches infinity 1 plus 3 over x to the 4x. Well, so in order to use the L'Hopital's rule, we have to have a quotient of a function in terms of a quotient. Well, that's not a quotient. That's actually a power, a function whose power is another function. However, we have logs, ln, basketball rule. No, it's smackdown rule here. Make that exponent equal the coefficient. And at the same time, I'm using the properties of limits in this case. One of the properties of limits says that if I find the limit of some logarithmic function is the same as finding the logarithm of the limit. It doesn't matter the order. And in fact, the latter will be more convenient. You'll see why. X approaches infinity. Alright. So number one, this is not yet the indeterminate form, so we can use the L'Hopital's rule because this is not yet a quotient between two functions, alright? However, this x right here, we can write it in the denominator of this natural log as ln of y equals to 4 times the limit of ln of 1 plus 3x to the negative 1, because we're about to differentiate. We can write this x in the denominator of this as x to the negative 1. And now we have a quotient here. We have a quotient. X approaches infinity. That means we can differentiate both sides. Alright? Well, no, not both sides. Actually, we're going to leave the L and Y as it is, because really the L'Hopital's rule only involves the numerator and denominator of the right hand side. So just leave the L and the Y alone. So the derivative of the numerator, that is the derivative of the natural log function, that is 4 times limit 1 over what's inside of the logarithmic function, which is 1 plus 3 x to the negative 1, times the derivative of 3x to the negative 1, which is negative 3x to the negative 2. So far, so good? Yes?
How did you get rid of the x from 4x?
Oh, this x, I sent it to the denominator as x to the negative 1.
Oh, how did you do that?
So for example, when you have 4 times 4, for example, you can write this as 4 times 1 over 4 to the negative 1. Alright? Same happens with the x right here, so we can obtain a quotient function to do the L'Hopital's rule. Right? And well, that's the derivative of the numerator. What's the derivative of the denominator? The derivative of x to the negative 1 is negative x to the negative 2. And I know this looks ugly, but check this out. A lot of stuff can cancel. We can divide out x to the negative 2 with x to the negative 2. We can divide the sign, negative over negative, that becomes a positive. And be careful with this 3. This 3 right here that was left in the cancellation, I'm going to multiply it with the 4 outside. Alright? I'm going to continue here. And yes, that's good. So that's, keep writing this as an equation, ln of y. Notice how we're going about this limit. We're not going along the line as in the previous example for these weird indeterminate forms. We treat the problem like an equation. You'll see why in a second. So 3 times 4 outside, that's a 12. Limit of 1 over 1 plus 3x to the negative 1, which is the same as 1 over 3 over x, as x approaches infinity. Alright? And in the denominator, well, that's essentially an invisible 1, but do we really need to write that invisible 1? Not really. Alright? Okay, so let's focus on the limit on the right hand side of this equation. So when we evaluate the limit at infinity, where is 3 over x rather going to go to? 0. Alright, that means ln of y equals 12 times 1 over 1 plus 0. 1 plus 0 in the denominator is 1. 1 over 1 is 1. 1 times 12 is ln of y equals to 12. But careful, we're not done yet. This is only ln of y. Alright? How do we get rid of y? Exponentiate both sides. Base e. So y equals e to the 12, which is equal to this limit. Alright? So that's the limit.
Do you have to denote that introduce L'Hopital's thing already?
Oh, right here. Oh, you mean to denote it? Yes, I think I forgot to write down that LH here. Yeah. Just to denote that at this point I did the L'Hopital. Yes?
One more question. Did you get 12 on the right?
Oh, yes. So when we cancel all this math, when we reduce all this madness here, we were left with this 3. That 3, we can write it outside, multiplying also with the 4. That's how we got a 12. Alright?
Isn't it like 12 like hard on
That either way, whenever you have like limit, good question. When you have limit of c f of x, some constant times f of x as x approaches some a. This is the same as saying C limit f of x approaches a. That's the multiple constant property. So you can have the constant outside, that is the limit of some number times a function is the limit of the function times c, right? It's, you know, like a commutative property. Good question, thank you. So that's the limit. Let's do one more. Is that the only one I have? Oh, one more? Really? Okay, limit x approaches 0, x to the 2x. So another power function, another function whose power is another function. So whenever you see something weird like this, call this y. You know, ultimately, this limit will be some number y that we will figure out as we go. So let me rewrite the whole problem. Oh, by the way, this is going to be 0 to the 2 times 0, which is 0 to the 0. That's the indeterminate form in this case, right? The 0 to the 0. But so that means L'Hopital's rule will apply. All right. So let me set up the limit again. Let me just rewrite this backwards. Y equals limit x approaches 0 from the right, and there's a reason why we have this x approaching 0 from the right. You'll see why. That's x to the 2x. And let's see. Let's take ln to both sides. That's going to leave us with ln of y equals, well, you can do the property of logarithms that the exponent becomes the coefficient to x ln of limit x approaches 0 from the right of x. And just the same way we did it in the previous example, we can interchange the ln with the limit, that is, introduce the ln operator to the limit expression. So ln of y, 2x limit of ln x as x approaches 0 from the right. So now you have an idea of why are we approaching 0 from the right? Because this just gave rise to a logarithmic function, and well, for the logarithmic function we can approach x only from the right, not from the left, because there's nothing to the left of ln. Otherwise, if I just say x approaching plain vanilla 0, well, I would need to check both sides of the limit, and there's points rather only to the right but not to the left. Question?
So what's stopping you from just like solving the limit with, because it's x is approaching 0 and it's x?
Uh-huh.
The ln of x is just 1, right? So
well, ln of 0, oh, let's find out. So number one, let's write it as a quotient first. So here is where we will need to analyze the functions for a while. Because, okay, well, ln of 0, what's ln of 0? Yes,
1, right?
the reverse. Ln of 1 equals 0, but if we observe the graph of ln, it's going to go to negative infinity. I mean, f of 0 is undefined. However, the limit approaching 0 is negative infinity. All right. Well, but we still need to check for one of the regular indeterminate forms the following way. Okay. So number one, ln of y equals to limit ln x over, okay, how about, well, number one, x to the negative 1, x approaches 0. All right, but isn't it true that this x to the negative 1, it's the same as ln y equals to limit ln x over 1 over x? Do we agree with this? Yes.
So how do you know to like turn it into a quotient and like go for L? Like why can't you just plug it in 0 and then?
Because ln of 0 ln of 0 is going to take us to negative infinity. So we're going to analyze this part by part. I'll show you in a second. So let's analyze the numerator. Let's analyze the denominator. All right. So x approaching 0 from the right. So let's analyze the graph of f of x equals ln of x. And the graph of f of x equals to 1 over x. So the graph of ln of x, which looks like this, and the graph of 1 over x, which is this graph right here. Alright? So individually, when we try to evaluate this limit at 0 but approaching from the right, so where are we getting on the ln function as we go 0 from the right? Isn't that negative infinity? Alright. What about approaching on the other function, 1 over x, approaching 0 from the right? Where is it going to? Alright, that means negative infinity over infinity, which is an indeterminate form, isn't it? It's weird, isn't it? But I mean, once you see all these pieces separately and you put them together, okay, that's it's weird how we go from 0 to the 0 to negative infinity over infinity. Yeah, it's magic. It's math, right? It's math rather. All right, that means we can go ahead and use the L'Hopital's rule. And I'm going to use the L'Hopital's rule not from this version, but actually from this version over here, the previous one. So ln y equals to 2 times the limit. What's the derivative of ln x? 1 over x. What's the derivative of x to the negative 1? So that's negative x to the negative 2 as x approaches 0 from the right. Okay, let's simplify this. I'm going to take this negative out of the limit and multiply it with the 2 so we don't have too many issues with it. So that's ln of y equals negative 2 limit. Okay, so that's 1 over x for now, being divided by x to the negative 2, which is how about 1 over x squared? Isn't it the same as x to the negative 2? 1 over x squared. All right. So negative 2 limit. Okay, dividing by a fraction is the same as multiplying by the reciprocal. That is 1 over x times x squared over 1 as x approaches 0 from the right. Well, let's keep going here. ln y equals to what's this? X squared over x. That's negative 2 limit x as x approaches 0 from the right. Well, what's the limit of x as x approaches 0? Times the negative 2. And that's 0. But that's not the answer. We need to exponentiate both sides. Cancel, cancel. What's e to the 0? 1. All right. Crazy, isn't it? I mean, it's nothing different from all the algebra that we have done all our lives, but it's the way we put it together and how we analyze all these individual pieces together. Question?
Yeah, at the end, when you input 0 approaching from right, can't we input 0.0001 or something like that?
Yeah, so in this case, this is really the diagonal line, y equals to x, so we're approaching 0 from the right, so that's getting to the origin, right? And this is 0.
Oh, so we don't have to use 0.00?
No need, because this one goes with by direct substitution. All right, guys.